Well, I can just start without the I don't need the PowerPoint to talk through it. Um, I guess the first thing that I would tell someone who is interested in modeling would be um, that the biggest difference with a modeling classroom and a traditional classroom that I have found is the way that material is presented. And in traditional classrooms, the teacher is kind of viewed as the owner of knowledge and the distributor of knowledge, and the person who decides if the student is right or if or not correct. And in a modeling classroom, the power, like most of that power, lies with the student. It's a student-driven classroom, and the teachers are there to facilitate and to guide. And it's very inquiry-based. It's very constructivist-based. Um, and that, I think, if someone were just to walk into a modeling classroom and just observe, I think that that would be the first thing that would strike them, is that the teacher's normally not in front of the classroom delivering content. That the students are, it's a very active classroom, it's very loud. The students are talking with each other, and they are discussing ideas, and they're debating ideas, and it's very interactive. So that's the biggest difference. If you were just to walk in out of a hallway and look into a classroom, that's what you would see. And then I'd say that the second biggest difference to a teacher who's used to teaching traditionally to look at what a modeling curriculum would look like for a full year is that the sequence is very different. So I am going to switch. You won't be able to see it, but I will. So I'm going to switch my presentation real quick because let me know if you can't see me. But when I first, I did a presentation for a local meeting, and one of the things I talked about was I actually used the Chem Chat on Twitter, and I asked, what do you think the goals of science education should be? And I asked the Chem Chat teachers, and I asked some mod chem teachers, and I asked some teachers I work with, and the biggest things, these were the highlights I got back. Number one, the most common response was that we should be cultivating love of science. We should be instilling a desire to understand why things happen. We should be helping students to develop critical thinking and problem-solving skills. And we should guide students in developing the ability to analyze and draw a conclusion and support their ideas with facts and data. And not just, I think this is why, but I don't really know how to explain why I feel this way. And then what I think is one of the most important goals of science education is to produce a scientifically literate population, because I feel like that is, these are students who are going to be voters soon, and please let them understand a little bit of science before they start making some policy. In traditional instruction, we're currently modeling a classroom environment where the teachers are asking all the questions. And to me, that's counterproductive. Young children are born natural scientists. They're inquisitive, they're curious, they want to know why things happen. And they ask those questions all the time. If you have children, then you know this, because toddlers, why? And my kids, still ask me why. What traditional instruction has done, it has beaten that curiosity out of them, because so many of our students are so afraid to be wrong.
Excuse me, sorry.
They're so afraid to be wrong that they are afraid to think outside the box or to propose an idea that might be crazy. And so they never want to ask the questions, and they wait for the teachers to ask the questions and to guide their investigations. Most of our students view us as the distributors of knowledge. They don't view themselves as owning their education, or even possessing the ability to deduce if something is correct or not correct, or even to have a novel thought. They're so worried about being wrong. Traditional education tends to reward students for sitting quietly and repeating back what has been told to them or what they've read in a book. That's not science. So what modeling instruction does is that it takes a constructivist approach. It immerses the students in the process of actually doing science instead of being told about science. And it provides them with opportunities to act like the scientists. It also builds a classroom culture where teachers aren't the owners of knowledge, that they're the guides. They help students construct knowledge mostly through investigation. So there's a modeling set of curriculum materials for chemistry, for physics, for physical science, and then the newest one is biology. I don't know if it's complete yet, but all of the curriculum materials revolve around a pedagogy and a cycle, which starts with observation, whether that's a paradigm lab in physics or it's the observing a scientific phenomenon, a discrepant event, something that they observe that then drives a question. They form a question about what they've observed. And then through discussion with their peers and their teacher, they try to develop a model that would explain what they saw. And once they've developed a model, then they start to test it, and they start to design their own investigations to test the model they've created. So they keep testing that, and we start providing them with new situations and scenarios to test it. We guide them through discussion and help them kind of create what they want to test. And then we test it, and we test that model until it fails. Because just like every scientific model, there are going to be limitations. And so we really push those limitations until that model fails. And when it fails, we use that information to evolve the model and to refine it and to make it better and to make it fit the new information we have. And then the cycle starts again. There's some tenets to modeling instruction. One of them is that we use multiple representations to communicate scientific ideas. And those multiple representations can be, we call them graphical, symbolic, pictorial, mathematical, and verbal. And a lot of those are done through whiteboarding sessions and through interaction with each other and with the instructor. We ask them to represent their knowledge in different ways so that we can try to pick out misconceptions. Whereas we might not see a misconception if they can represent mathematically what they're thinking, they could get the right answer. But then for them to explain that same concept with a picture, it might open up a whole new level of information for the instructor to see, and then address any misconceptions that come out of that. We use scientific questioning to guide our investigations. We design investigations to collect data, and then we analyze and evaluate the data. We work with scientific theories and multiple explanations, and we connect content across domains. Now, that should sound familiar to you if you are teaching AP, because those are the 7 science practices that College Board says students should be engaged in. They align very nicely with modeling. In traditional instruction, we tend to begin with atomic structure. So I'm going to come back and let me see what's going on here. So Jill and Amy, you're the only ones I can see right now, but I do have 4 of you. All right, 4 people. Jill, where do you start? Because you're a classroom teacher, correct?
Yes.
Okay. What's the first unit you teach?
We do experimental design.
Okay, so scientific method.
And then we move on to do chemistry fundamentals.
Okay.
We do a little bit of periodic table, a little bit of nomenclature, a little bit of reactions. We don't get to atom until 3rd quarter.
Oh, okay. So you don't get to atomic models until 3rd quarter?
Yeah, we don't get to it till later on. We go ahead and do a lot more focusing on big picture, physical chemical changes, states of matter, the energy associated with those gases, and then we come back and pick up the atom and the quantum model and things like that. So we don't do electron configurations or trends until the very end.
Well, that's actually not too far off of the modeling sequence. In the modeling sequence, we actually follow we follow chronologically the discovery of the particle theory of matter and how it evolves over time. In the research I've done, most traditional classrooms do atomic model very early. Yeah. And they start talking about protons, neutrons, electrons really early on so that they can jump into nomenclature and stoichiometry. I'll get to the sequence that we follow. And Kristen, hi Kristen, I saw your question. I'll get to it in just a second. In one of the things, my favorite things about modeling is that we focus on conceptual problem solving, and like I don't give equations. All of my students solve problems based on relationships that we discover in lab, and gas laws are one of the first things that we do, and so I don't ever give them P1V1 equals P2V2. My students understand that if pressure goes up, that volume had to have gone down, and so they don't need an equation. They can just they look at the data and they realize, like, they start to see, oh, it's directly proportional, or it's indirectly proportional, and then they can arrive at mathematical or quantitative answers from understanding relationships instead of just plugging things into an equation and solving. Because what I found is I've got kids that are really good at algebra that can get a right answer and have no concept as to why or how that answer is right. Let me go back to Kristen's question. Hang on. Kristen says, how long does it typically take students to get the hang of creating their own models? Well, real early, because I make them start right away. So one of the very first things that we do is the very first lab of the entire year is matter and change. And so they investigate, it's 6 different things they investigate. For example, they weigh sugar, dry, and they weigh a vial of water. And that's their system. It's all of that together. And then they dissolve the sugar in the water. So macroscopically, they see that there's no sugar left. But the data they collect is that the mass didn't change. We do, and that's not a surprise to most of them. It's not. We do a precipitation event where they take two reagents and mix them together, and they're 2 clear colorless solutions, mix them together, white precipitate. Many kids will predict that will weigh more, and then they weigh it and realize that it doesn't. So we're building on this idea that in order for a mass change to occur, something has to be added to or taken out of the system. What gets them is the very last one that they do, and it's when they burn steel wool, because most of the kids assume that it's going to weigh less because they've seen that when things burn, they get smaller. But what happens with steel wool when you burn it is that oxygen gets added in, so it actually weighs more, significantly more. And so we talk about that, and they have to postulate why that happened and what could have been added in. So it really doesn't take long for them to start building their model. Now, Kristen, their first model is that matter is made of particles, and that particles are individual little, they look like BBs. They could be squares or triangles or whatever in their pictures. We try to get them to move towards circles because that makes it easier for us as we move through. But the models are very simple to begin with. The very next thing that we do in the next unit is we look at gases, and the first discrepant event that we look at is you can make popcorn or you can burn a candle, and we have the kids notice that the smell travels through air. And so how did that happen? And eventually we come through, there's a big discussion, but eventually we get to the point that, well, particles must move. And that's a new piece to our model. And so now our model is of particles that are these hard spheres that are they are not divisible, and now we know they move. We have evidence that they move. So developing the model is not difficult for them because we start very simply. The model evolves and gets more complex as we add more pieces to it. Doug says, what does the typical day look like in the modeling classroom, particularly the start of class? Well, it depends on where we are in the unit. If it's day 1 of a new unit, it's going to start with a demonstration. Usually demonstration, sometimes a lab but we will discuss a question that's been posed. And then through the class discussion, we'll talk about how we can test different things. Like on day 1 of on the first day of the lab for gases, we open up a bag of popcorn and we let them raise their hand when they can smell it. So the students then realize that the particles have moved, and then they start discussing that. Well, then we move, and that's with gases. And then we move directly into cold water and hot water, and we put food coloring in both, and we watch how the particles of color move through the different the two different beakers. And we don't tell the students that one's hot and one's cold, and they start to give us ideas as to why one's moving faster than the other. So that's what like the very first day would look like. If you were to come in the middle of a unit, you would probably see whiteboarding. I would give the students perhaps, like, if we're talking about energy or what the quantitative heat problems, what most teachers would use Q equals MC delta T for, I might have like a problem set that the kids are working on, but they're sitting in groups and they have a whiteboard in front of them and they're discussing different ideas and they're drawing graphs that are informing how they're going to problem solve, and they're arguing with each other and they're defending their thoughts, and sometimes they're holding up their boards and presenting it to the class, and they're talking to each other, they're asking me what I think, I'm telling them, you know, I'm trying to ask them questions to guide their thinking in the right direction. Let's see. We're doing a lot of hands-on in the laboratory. We're doing a lot of analysis of data, but it's always together in a group. We do assessments, and those are individual, and that we do. We review. We try to like bring all of the unit back around together and make it cohesive. And we let the kids ask questions if they have any, and then there is an assessment at the end. And different modelers have different theories on assessment. I'm leaning more towards standards-based assessment, but not everybody does that. Doug, is that? I hope that answered your question. Let me know if it didn't. Send me another one. Let's see. Kristen says, good examples of changes. Those are all good types of reaction changes that we did in introductory physical science that I taught when I first started, perhaps a precursor to modeling. Perhaps, yes. Some people make the argument that they see what we do, especially if someone comes to a workshop and only stays for the first week or only like sees one of the earlier units. And I've had people say, oh, but modeling, that's baby chemistry. It's too easy for what we do. We can't, you know, how do we prepare the kids for the upper level courses? And I say, stick around because it does get more challenging. Our quantitative heat problems are ones where previously I would only see it in an AP curriculum. When I taught regular Chem 1 before modeling, I would only, if I was giving them a Q equals MC delta T problem, for example, I'd ask them to perhaps solve for heat or perhaps solve for mass, maybe. And in modeling, I can ask them to solve for heat, I can ask them to solve for mass, or what portion of mass would be boiled away or melted or whatever. I can ask for how much of a temperature change would happen, how much of something would increase in temperature after it's melted. These are problems that are very tough, even for teachers. I'm in the middle of a workshop right now, and even the teachers are looking at these problems, and it's been a while since they've done them. So we do get into challenging concepts. We do equilibrium through modeling. It makes them understand at a particle level what's happening instead of just I can plug and chug numbers. Johnstone, some of you may have read Johnstone, or Dorothy Gable has a really nice article out there that incorporates the Johnstone triangle of understanding, where there are 3 levels of understanding. There's macroscopic, what she calls submicroscopic, what I would call particulate, and then symbolic. And research has shown that teachers of chemistry or adults, we move very easily between symbolic and macro. Like if I were to write NaCl on a board, like you and I would know that that means sodium chloride and that it's probably referencing 1 mole of sodium chloride if it's in an equation or something like that. But the student doesn't know if that means 1 atom, if that means 1 mole, if it means 1 gram. They couldn't draw it for you. They don't know what it looks like. And so what we found is we have to make those connections for them, especially between the macro and the particulate, or the symbolic and the particulate. Making those connections really helps to build the student's technical understanding. Oh, Luann's here.
Yay!
Yay! She's asking if we're here. I hope she can see us. We're on, Luann, if you can't see or hear us, we're on, maybe Jill or Amy, maybe you could send Luann a link.
I'm sending it to Luann right now.
Thanks. I got that one too. Okay, so I've taken care of all the questions, so keep them coming if you guys are still there. It says I have 5 viewers. Yay! Let's see. Sequence is a big, and pacing.
She says her satellite connection doesn't like Google Hangout.
Oh, well, boo on satellite connection. Pacing is an issue. I will tell you that I quote unquote covered more material before I taught modeling, and my modeling trainer will tell me what is the definition of cover. It means to obscure from view. And so I'm sure I did a lot of obscuring from view when I went very quickly through material instead of really getting into this, the concepts behind them. My first unit in modeling, it lasts at least a month, and that covers mass, it covers volume, it covers density. And I build a classroom culture, and my students learn how to whiteboard, and my students start to learn that they can trust themselves, and they can start to learn to think for themselves, and they start to learn how to verbalize mathematical relationships and make meaning from them. So although it is a very long unit, it's very important. I got a question on Twitter from Bridget. It says, in my opinion, is it an all or nothing approach? Tried implementing some in AP this year, went to add in lower levels. So Bridget, hope you can hear me. It's not all or nothing. I happen to be very lucky in the school that I'm at. I'm a small private school, and I went there because I could implement modeling completely. They gave me that freedom. So my very first year, I was in a public school, and I happened to have only one other person teaching chemistry with me, and she had been to the modeling workshop with me, and so we went all in right away. It was very challenging. I had been teaching for a full decade when I did that, and I completely changed everything I did. I threw away all my old stuff, literally threw it away and started over, and committed to modeling because I knew that I knew it was going to be hard, and I knew that if I had my other stuff still there I could refer back to, that I would do that, and I wanted to give it a chance. I work with some really amazing teachers in Indiana. One in particular works at the largest high school in Indiana, and he's one of, I think, 12 chemistry teachers, and he's the only one that wants to model. So what he's had to do is he has to follow their sequence because they switch students at semester and they have common assessments. So he implements the pedagogy all the time, but he implements the materials when he can. So he has to go in their order, which means he can't do everything that we do, but anytime he can, he throws in a modeling approach. If you can just build in the conceptual stuff as you move, you're going to be doing better by your students that way. And so, Bridget, if you are looking for someone to collaborate with, I can connect you with him, and we can also talk offline about ways that you can implement pieces of it. Whiteboarding and including particulate diagrams is one of the easiest things that you can do if you want to start slow. Kristen has a question that says, what sort of challenges did you have to overcome as a teacher when you switched? Timing. Yeah. Recognizing that I definitely had, let's see, I had to admit that I didn't know everything I needed to know about chemistry. And there was a lot, I had a lot of misconceptions myself that going through the modeling training helped me to understand chemistry a lot better. I know more science now than I did before I started modeling workshops. So pacing and sequence were really tough. Let's see. The biggest challenge would probably be I don't get to talk about the periodic table as much as I'd like to. And getting students to buy in. That's tough. Getting students to buy in because it is very uncomfortable for them to not know all the answers all the time. And so building the culture is really important. And letting the kids know it's okay to be wrong, and making it a safe space in your classroom for kids to make mistakes, and reinforcing that as often as you can. That science doesn't progress until mistakes are made, because we don't learn anything if what we expect to happen happens every time. And then there's some materials on the AMTA website to help you talk to parents and talk to administrators about why you're making the choices you are, because that can parents think that education should be what they like. A lot of them are like, well, that's not how I learned chemistry, and I turned out okay. Well, our students are changing. Our students are, it's a different generation. They don't learn as well just sitting in a classroom and being lectured to. Teachers tend to teach how they were taught, and none of us were probably taught with modeling. So it's uncomfortable for us, and it's uncomfortable for the students in the beginning, and that's when real change is made. Once you're uncomfortable, then you start to see that you can grow. And once I saw modeling and I saw what it could do for my students, even though I knew it was going to be harder in the beginning, I couldn't keep doing what I was doing because it wasn't the best way, and I knew that, and I just couldn't reconcile that with myself, that I knew there was a better way, but I was going to choose the easier way. I couldn't do it anymore. Let's see, I've got another question on Twitter. Let's see, how do parents respond to modeling? Well, that's a good question. Parents, it can go either way. Some of them are very worried that their kids aren't going to be prepared for AP, or they're not going to be prepared for college chemistry. But I have pages and pages and pages of research that you can always reference, and you can always show to the teachers or show to the parents. Make sure you're informed. Make sure that you can back up what you're doing. I journal a lot, and so I would think I would be writing down these things as they would come to me. Like if I could put onto paper why I'm choosing modeling, can I actually verbalize it? Can I write it down? That helped to focus what I would say when the conversations happen. I didn't get a lot of pushback from parents. I really didn't. But I also started doing this in a school where I had already developed a reputation, and I'd been there for 10 years. So that was helpful. The kids do give you some pushback. And so you have to be encouraging at all times. And you make it fun, and you make it engaging, and then they start to see that you're on their side, you guys are in it together, and you're working towards a common goal. It takes some work to build that culture, but a lot of us, if we're passionate about what we're doing anyway, we're halfway there. I mean, we've already started to do that. Let's see, getting more on Twitter. Let's see. Let's see.
Did you see Ramsey's post?
Am I seeing whose post?
Ramsey's post.
Yeah, I'm seeing that right now. It says, are you familiar with anyone who has successfully done modeling in the context of AP, specifically the revised curriculum? I'm working with Carlos Montero right now. Carlos, actually, that's why I'm in Florida. I'm with Carlos. Carlos is a modeler. He's actually on the board. He's a counselor. I forget his title. He just won the presidential, the PAEMST, the one where you get a nice size check and you get to meet Obama. He just won that award for the state of Florida. He also just got his AP scores back, and I don't think he had anything lower than a 4. And he incorporates modeling whenever he can in AP. And his first year at the school he's at now, he just told me that he went through the entire AP, or he went through the entire modeling curriculum, including, and so if Ramsey is familiar with the modeling curriculum, there are core units. Units 1 through 9 are core, and then beyond that are the more advanced units like entropy and equilibria and things like that. And so Carlos did all of the materials with his AP class. That was his AP class. And he went into more detail when necessary. But what he had inherited when he moved schools were students who had never had any modeling at all. And so his first year there with AP, he just did all modeling throughout. He went through the whole curriculum and supplemented when necessary. Now that he's been there, the students who take his AP class have already had modeling, so he doesn't need to go through the whole thing. But I asked Carlos today if he knew Ramsey, and he said he did not. Carlos is not as active on Twitter as we are, but I can definitely connect the two of you, and you guys can chat. I know he's very interested in developing more materials for AP incorporating modeling techniques. So if someone's willing to collaborate with him on that, he would be thrilled. think I got all the questions, so keep them coming unless, let's see. Yep, I don't have any more on Twitter yet either. Are we done? We answered all the questions? Okay.
I'm looking through to see.
Are you seeing any more? Okay. I can tell you, if you're looking to learn more about modeling, if you haven't taken a workshop yet, that's where it's the best decision I ever made professionally. I learned so much, and I connected with the most amazing teachers, and some of those relationships that I made in my very first modeling workshop have persisted. I've grown as a person, I've grown as a teacher. I think I'm a better mom because of them, because they taught me patience. Really, if you can, get into a modeling workshop. All of the modeling workshops are posted on the AMTA website, which is in the links on the page that you're looking at. But it's just www.modelinginstruction.org. You can see when they are offered. Most of the time they're offered in the summer. Sometimes they have a fee associated with them. Sometimes the participants get paid. Let's see. To join AMTA, you can join AMTA without having taken a workshop, and you would have access to the curricular materials, and it's $60 a year to join. You can follow them on Twitter. AMTA. It's better to follow the hashtags because they're more active than the actual AMTA website. But it's hashtag ModChem, hashtag ModPhys, and hashtag ModBio. The physics curriculum has been around a lot longer than the chemistry one has, so that that community is larger. You can actually get on. You can join the listserv without having to be a member, and you can follow along with discussions and things like that. Let's see. Kristen says, "I'll be the annoying kid who always raises their hand. Can you list the core topics and units?" Yeah, I can do that. Hang on one second. Let me switch to my other screen. So the topics go in order. Physical properties of matter. The second one is energies and states of matter, part 1. That's gases. So in Unit 1, we established that matter is made of particles, that the particles have mass, they have volume, and that they can pack differently, like in solids, liquids, and gases. And then in Unit 2, we start talking about how gases move, and then how particles move in liquids and solids. And we start talking about the concept of energy. And then in Unit 3, we start talking about phase changes and different mechanisms in which different storage accounts that energy can be stored into and transfer between. Excuse me. Then we move into describing substances. So after we establish that matter is made of particles, particles can move, they can pack differently, they can change phase, the energy is associated with the particle movement and with phase changes. Then we start talking about classification and nomenclature. So that's when we move. That's when we start talking elements, mixtures, compounds. Then we go into particles that are too small to see, and that's when we introduce the mole concept. That would end my first semester. That's as far as I get. I do not have as much instructional time as a standard K-12 teacher because of the type of school I teach in. So then my second semester, after January term is over, so I lose 3 weeks, I get the internal structure and bonding. So that is going to be ionic and covalent bonding, interaction between particles in a bond. Then we move into chemical reactions, and then we do Stoich 1 and Stoich 2, which includes everything that you would know about stoichiometry, and we throw in gases, like the ideal gas law, only we don't call it that, and energy changes. So like enthalpy is in that unit. And the very last thing in the core units would be models of the atom. So we talk, the majority of our time we spend in Dalton and Thomson. So the Dalton model stays with us for a very long time. We start Democritus, it's there for a while, Dalton's there for a long time, and then we get plum pudding. And we stay in plum pudding because plum pudding does a pretty darn good job of explaining matter until we get to the Bohr model. So let me switch back to you guys, and I think I got that. Kristen, let me know if you want more. I can actually share that document with you if you'd like to see it. Let's see. I had a bunch of Twitter things come across, and I missed most of them, so let me see. Okay, let's see. Jill, are you seeing anything?
Ramsey had a question about equilibrium.
Oh,
If there was an example you could give using equilibrium.
so I can, speaking of connections, Ramsey, I've got someone you have to talk to. His name is Jeremy, and he teaches in Indiana with me, and he has developed some modeling type materials for equilibrium that aren't incorporated into AMTA yet, but he would be happy to share them with you because he's looking for feedback. So if you're familiar with the equilibrium unit in modeling, the equilibrium deals with phase equilibria and moving between two phases. But in Indiana, at least, a lot of teachers have to talk about dynamic equilibrium, chemical equilibrium with like reactions. And so Jeremy developed some really cool materials based on 2 or 3 different articles he read from the Journal of Chem Ed. And his materials involve particle diagrams and graphing, and he did this awesome stuff. And I will, if you DM me your email address, I can share those. I can share that with you, and then I can connect you guys on Twitter because he's looking for feedback, and I think he would really like to connect with you about that. So hopefully that's helpful, and I will make a note to get you guys connected and to share that with you. Just DM me your email address. Let's see.
IB Chem Ninja. So there was an activity where you could use model kits, paper clips, and rubber bands.
I have seen that activity. That is a Target Inquiry. That is available on Target Inquiry, and I believe that's Scott. I think that's his Twitter name. Yeah, that is an activity I have seen. It's about, and so correct me if I'm wrong, Scott, but I think it's about how energy is stored, or...
He says then you graph the rates and concentration over time for reactant-driven.
Okay, no, I'm thinking of a different one. I know Scott had said that and I apologize if that's not who that is, but I think it is. He had some materials that he wanted to share, so maybe he can start posting links to that using the hashtag ChemChat, and people can get those materials there. Or he could host, he could host a Google Hangout, and he can figure out how to do this, because we are making it up as we go along. And then I think someone told me they DM'd me, and I have 19 Twitter notifications. Let's see.
A lot of those notifications are just us talking back and forth.
Yeah. I know. So if someone said they DM'd me and I didn't get it, so you might want to try again. Yeah. And I will definitely connect Jeremy with Ramsey. So if anyone's going to be at Chem Ed conference, there's going to be a really large group of modelers there that I'm sure that we would all like to connect. So make sure that, and we have several different presentations planned about modeling, so you can get more questions answered. People that have been doing it longer than I have. Larry Dukerich is going to be there, and Larry helped to develop a lot of these materials. I think Ramsey's going to be there. I thought I saw his name on some presentation. I'm not seeing any more questions come across Twitter. Of course, I say that, and I'm going to get 13 now. So, we might be wrapping up. So those of you that I can see, Amy and Jill, are there? Do you guys have any questions did you have any prepared that I didn't get to, or?
Nope.
No? Okay.
Do you know of anybody who is doing this in a school system where there is an end-of-course test?
Yes. Most of the teachers, they're very common now. So, like I said, some teachers that I know can only pick and choose and put things in when it fits their prescribed sequence. I don't know about across the country, but in Indiana, if you're looking for an end-of-course assessment, you have options to create your own, or you can use one that's already been created. And I can tell you that ACS has previously had a conceptual high school chemistry exam, and it was last updated in the early 90s. And so I'm on the test writing committee, and Laura Slocum, who is a modeler from Indiana and is now in South Carolina, Laura is the chairperson for that. That test went into testing this spring, and so that's why I'm going to Chem Ed. So before ChemEd starts, I'll be down there, and we're going to compile all the data we collected from the pilots, and we'll look at each question. And so we're going to be evaluating the questions we wrote and the exam, and then soon that exam will be available. So if you need to have a standardized, like, end-of-course assessment that would address modeling, it also works with POGL. So because we have POGL teachers on that committee as well, because we were trying to incorporate as many people that taught conceptually as we could. So we've got ChemCom people, we've got POGL people, we've got modeling people. So there are questions out there. There's a test out there you're going to have, like, you can compare to national averages and things like that if you need to have a test like that.
I'm sorry, I guess I just wasn't clear. Virginia has an end-of-course chemistry test.
Like a state-written one?
We have a state-written where I think there's like 10 states left when I looked 2 or 3 years ago that still do a chem-specific test. I'm one of those. And so I just wondered if you knew of anybody else who was in a similar situation who had attempted to do modeling more full speed ahead as opposed to pick and choose.
Can you
was with
tell
that
me
setup.
If you know the states that would affect?
I know at the time when I looked, California had one, Texas had one, New York has one, obviously.
Oh, New York has one? Oh, then yes.
New York has regents.
Yeah, there is a huge population of modelers in New York.
Now, I think you can offer chem that's not regents-based in New York, and you can offer chem that is regents-based.
Okay, so then what I would say to you, do you know Frank Casey?
I know of him, yeah.
Okay, so he's a modeler.
Yeah, he does physics.
Yeah, and chemistry. I think I know he does physics, but he's engaged with me with some chemistry stuff. He may not be teaching it, but he's familiar with it.
Okay.
So if you tweet him, he tweets you back.
Right. So no, I know him. Yeah.
Yeah. So he would be one to ask. And New York hosts one of the largest modeling academies or groups of modeling workshops. New York hosts one of the largest ones in the country. So, and then some of them are chemistry. There are teachers in New York that are definitely integrating full model. And I'm not one of them, but that's you could connect with somebody on
I'll talk to Frank.
Yeah, Frank would know. Let's see. I got some more things. Okay. Storm moving through kicked Amy off.
Yeah, I saw Amy disappeared on us.
Yeah. It's been, at least we got rain in Florida today. Haven't had rain in Florida for a while. Okay, so I've got some emails to write. It's about 9:15, so I'm ready to wrap up unless some more questions come through. It's kind of died down, and so I'm thinking that maybe I either confused everybody, people got sick of listening to my voice, or we're finishing up.
No, I put out a tweet and asked if people had any other questions, and I haven't heard anything back.
Okay. So what I would say is follow me on Twitter. Feel free to email me. So if you see me on Twitter, then you will know my email address. But it's erica.a.posthuma, P as in Paul, OSTHUMA @gmail.com. And I can connect you with people like what you've heard me do. Like, I may not know this, but I know someone that does. I will connect you with those people who would love to collaborate with you. And if I can answer your questions, I will. But I'm also going to be at ChemEd. I'll be working the ChemEdX booth with Doug Reagan on Wednesday, the Wednesday of, I think it's Wednesday, right, Doug? The Wednesday evening of ChemEd. I'll be there, so you can stop by and talk to me about that. Yeah, there's Doug. Did I see? Yes, I got that. We answered that. Doug, if you're looking for equilibrium stuff, I can connect you with my guy too, so let me know. But I think that I got that. Let's see.
Ramsey said...
I think that was directed at Scott.
Ramsey... Oh, okay. Oh, I see. I become Milam. Okay. One other question I just thought of when you were talking, and thank you again so much for doing this. It's been awesome.
I hope that it was helpful.
Is there with the modeling curriculum that's available on the AMTA site, is there suggested amounts of time to spend on certain activities, more of a pacing guide or anything like that, or is that something you get more at the workshops?
There's really not like a modeling endorsed pacing guide, because I think, well, like I mean, I'm on a modified block. I have 3 days where I teach 50 minutes, and then 1 day I teach 75. And some, like Carlos has, he's got like 15-minute periods every day, and then in AP he's got 2 hours every day. So it's not, since it's not unified across the country, we don't really have like a pacing guide, but we also don't want to put people in a box so much. Like sometimes your kids just need to spend a little more time on density. You know, like once you start to do the curriculum, you'll start to see, or you start to do the instructional method, like you start to see, you notice when your kids need a little more time on something. And I think that locking yourself into a pacing guide, I know that some schools make you do that. It can really inhibit the learning. But when you take a workshop, you will be instructed by someone who's a master teacher who's been doing it for a long time, and they can give you what they do, and they can give you pacing. Like if someone were to ask me, I would have to find out like what type of students you have. You know, is it honors? Is it regular? Do you have students who have you know, are you mixed class where you have students that possibly have learning challenges mixed in with students who are accelerated? I would need to know, like, do your kids have algebra? Have they taken algebra yet? Have they taken physics yet? Are you physics first? So all of that kind of feeds into how long it's going to take. But the community is here to help. And so if you are looking for how long should this take, or how can I make this go faster, or where should I spend my time, those are questions that you would ask somebody that is familiar with your situation and has been doing it for a while. That's what I would say. And the workshops are where you make those connections for sure.
Okay. No, I totally get that. I was just more wondering if there were any recommended amounts of time, things like that.
Yeah, I wish there was. I wish somebody would tell me if I'm spending too much time on something. That's a common question. People are worried about that a lot.
Well, I just was curious because I hadn't heard anything about it, and I didn't know, and I'm totally like, yes, rigid. You spend X amount of days on a certain thing. No. But I didn't know if there was any recommended or suggested, like if you want to try to get through the 9 units, you know, this would be approximately, this is typically what people spend time on in this first unit. That's all.
Yeah, I would say that what you just said is the pacing guide. Like most teachers try to get through the 9 core units. My first year doing it, even though I definitely had more instructional time than I do now, it was tough, because I was going so slow, because I was kind of learning how to do the Socratic dialogue and to manage the scientific discourse. I was doing that at the same time as implementing all new curricular materials. So, but I would say if you can get to the first 9 and supplementing into things you have to put in there because your state says that you have to, like we don't teach electron configurations, but some states make you do that. So you got to figure out where to shove, you know, where to fit. And people have got suggestions for you as to where that fits the best, but I would say getting through the first 9 would be a goal.
All right, and one last question I just thought of, and then I promise I'll leave you alone. You talked about some people that were POGLers that have been involved with this. How do they still do POGL along with modeling, and if so, how do they make that work out?
I think, and I don't know too many. I know Kristen does POGL, and I do POGL. I'm gonna do more POGL in AP now. I think that they're just the ones I've talked to were taking some of our demos and some of our activities and just integrating them into where they fit in the curriculum they already had established, and then integrating techniques like whiteboarding and using whiteboarding and particulate level drawing and those multiple representations of knowledge, just kind of peppering that into the activities that they already had.
Okay.
Yeah.
All right, because yeah, this was the first I've ever heard of anybody not doing modeling full out. I've always been.
Oh, really?
Yeah, I've always been told it's pretty much you go all in and that's about it.
Yeah, no, I know a lot of people that just don't have that. I mean, I have a lot of friends that did all in, and that's what I did because I had that freedom. But I understand that there are limitations placed on a lot of teachers, and they can't fully integrate for a multitude of reasons. And I think that just doing as much as you can when you can is beneficial.
Right.
Yep. So I think we did it.
Yeah, I don't think I see anything else. Thank you again so much for doing this.
Well,
We
thanks
really
for asking
appreciate it.
I hope it helped.
No, it's awesome.
Okay. Well, it was nice to meet you, even if it was just on video.
It was nice to meet you as well. I can't see you anymore, but it was nice to talk with you.
Okay. I will talk to you later.
All right. Bye-bye.
Bye.